Hey guys, this is Tom Cherryholmes with the FujiNet project, and here we have a status report as of March 21st. I wanted to stop here and kind of show now that most of the functionality has actually been implemented and the various test programs have been wound down, where a lot of our time is actually being spent. And it's in the details, rolling up our sleeves and trying to make what we have written a lot more reliable. We'll go ahead and just kind of take a look at some of the things that we've been doing here. And you can see we have open an implementation of our TNFS code and the implementation of our TNFS code. And inside we see a variety of different functions for implementing everything that the TNFS file system object needs in order to act as a standard Arduino file system object. Things like reading and writing to files, opening and closing, etc. And if we look down here, we see the dichotomy of the TNFS file implementation API that we have to implement so that Arduino is happy, and the raw TNFS file system code itself. Now previously, we had implemented inside each TNFS open call, close call, read, write, its own logic for formulating the packet, sending that packet out, and dealing with retries. We did this initially because we were trying to get something up and running as fast as possible, so we wound up doing essentially cut and paste of the code to various functions just to get something running. But it caused a bit of a problem. You see, as we started understanding the nature of what errors we had to trap and when we had to trap them, these implementations of what ultimately became the TNFS transaction function, which we see up here if we go to it, started to get out of sync. So as part of the refactoring that we needed to do, it became clear that we needed to take the common logic for sending and receiving TNFS packets, which get transmitted over UDP, to one place so that we could actually take and track down the bugs that were happening and to refine the retry logic as we need it. So now all that retry logic has been pulled out of each of these individual functions. It's sitting here in TNFS transaction. What are we having to check for here? Well, if you notice, we have essentially we're sending each transaction to a host, to a port, and packets of variable length that we have to deal with. We have to deal with these packets in the context of a certain number of retries, which we currently have set to a maximum of 5 retries inside the code. We start the retry, we take the packet as it has been formulated outside of this function, we dump it to the console so that we can see it as we're doing development, sending off the packets, and then essentially waiting for a response. And if the response comes back, then we do something with it. Now, you heard me mention that that TNFS uses UDP. And for those of you who are not familiar with how UDP works, UDP is, at its most basic level, a raw packet sent over Internet Protocol. Why is this important? Well, we're dealing with a packet switch network, which means we're taking the information that we want to send from one place to another, and we're breaking it up into small bits and pieces, which we call packets. And we're sending them along what we consider to be the best path to go, that we can think of, to go from one place to the next. Now, for most people, that basically entails sending it to your router, the router sending it to the next upstream router, And at each point, the routers at each point checking the destination of that packet and determining the best course of action for where to send it to the next upstream router that it knows about, until eventually that packet comes down to the other person's router at the other end of their line and to their target computer. This is very much oversimplified, but I'm trying to keep it as simple as I possibly can. It is also worth noting that the internet is what can be described as a best effort network. That is, there is no guarantee that a packet will make it from one point to the other. And this is especially true with UDP. Because of this, we may have a situation where a packet will literally time out before our timeout reaches, and we will try to ask for another, and we'll try to send another request. Now, in the meantime, one of two things may happen. One of several things may happen, but the most common actually being that either we don't receive a response back at all, or we may actually receive that response at a later time after we've received other data. That is, we might actually get the responses out of order. And if that's the case, then we need to actually deal with that effectively. And in our case, it really is as simple as checking to make sure in each TNFS packet there is what is called a retry counter that gets incremented each time a successful packet happens. We check that. If it doesn't match the packet that we're expecting, we ignore it and let our retry logic actually handle the problem. And for the most part, this is actually helping. I think we can take and strengthen this a bit more, but that's essentially the essence of what we're having to handle. So if we actually take a look, we can see that we have, as part of our TNFS packet, let's go to our declaration if we can. May actually need to. TNFS packet T. Can I? This is what I get. I'm still learning the ins and outs of this particular editor here. Let's go down a little bit and take a look. Okay. This is what I get for improvising. Somewhere in here I have my TNFS packet implementation, which has our TNFS packet type. Right here. So each TNFS packet, if you look at the protocol declaration, you'll see that it consists of 2 bytes, which comprise a session ID, 16-bit session ID, and we have a retry count. We also have a command which indicates the type of command that we're going to be issuing, either, open, close, read, write, etc. And finally, the payload that we're going to send. Now, because the MTU, the maximum transmit unit that most routers can actually receive and transmit consistently is actually quite low, we're having to keep the size of our UDP packet at or below 512 bytes in total, so that we do not risk the upstream router fragmenting the packet and forcing us to have to take and implement defragmentation logic. But the thing that we're interested in here is the retry count. And if we actually dig in and look at the retry count and how it's used, we can see in the TNFS implementation here, the transactions for the low-level functions, we are basically essentially checking to make sure that our current retry count, which we grab from the packet that we most recently transmit, if it doesn't match for whatever reason, we assume that the packet is out of order and that one of our previous requests came back to us a long time after the fact, and we just ignore it and let the retry logic essentially handle what it needs to handle. Now, essentially what happens here, for each TNFS transaction, we send the packet, we wait a certain amount of time, which in this case, 5,000 milliseconds, roughly 5 seconds, at which point we give the opportunity to take and yield so that other parts of the microcontroller can do what it needs to do. But we're waiting for a packet to come through. And if the packet comes through, we unpack it, read it, unpack it. We go ahead and send it out to the debug console, which we'll see in just a moment. And we check for the retry count. If it's not there, if it doesn't match, then we simply ignore it. Otherwise, we return that that we did receive a packet. Now this is important because if you notice, our return value merely specifies whether or not we received a packet or not. The actual checking of the validity of that packet is done in the function that calls TNFS transaction. Now, with that, we keep trying, readjusting the retry count back to the same value until the number of retries that we were going to try exhausts, and then we say, okay, we just couldn't do it. We didn't receive a packet for whatever reason, and we simply return false, and that's the end of it. But because of that, it drastically simplifies the logic that we need to do for each of our functions to limit it to basically forming the packet that we want to receive and transmit, and then checking to make sure that things are correct or if they're not. Now, of course, there's plenty more that we can do. We can further program more defensively in the event of other errors, and that will come. But the first major step had to be done here. Again, for the unmount, much the same pattern. We do the transaction, otherwise we return false. And again, down in the open. Now the main differences between the mount and unmount and the rest of the functions has to do with the usage of, for example, the TNFS implementation object here, which is basically a pointer to the TNFS implementation objects that you see here, so that we can get access to those bits of internal state that we need for those. Open, close, open directory, close directory. And it makes each of these functions much simpler, much easier to track through for us to be able to figure out what to do next. Now, as part of this, I actually, now that we're down to the TNFS read function here, now that we're actually down here, I want to point something out. And that is that basically that we have a read cache, but it's not implemented here. This TNFS read only deals with a single read request to the TNFS server. The read cache is actually implemented in the SIO disk object. And if we take a look at it, we can see that we have logic here for what is essentially uncached region, which by default, this is 3 sectors. I did this to simplify the read logic quite considerably because if you recall, on most Atari disks, the first 3 sectors of any disk are 128 bytes in length, regardless of the sector size of all the other sectors on the disk. And we need to account for that. And if that's the case, then we take and adjust appropriately. If it's a double density disk, then we need to take and do bias and offset adjustments here so that our offsets for our seek command actually wind up in the right place. Now the reason I actually implemented this as a define, if we set this all the way up to 65,535, it actually disables the cache completely and is very helpful for tracking down issues with the underlying TNFS implementation. And in fact, that is exactly how I managed to track down some of the errors that we were having in the TNFS code. So with that, we can go ahead and for this next particular, for this particular demonstration, we are actually going to change our uncached region to 65535. We're going to upload the result and monitor what happens. Let's just go ahead and redo that. Overall, I have to say I'm very happy with Platform IO. Yes, it does take a bit more to get running. However, it's more efficient once you're up and running. Both in terms of it doesn't try to rebuild everything every single time. It implements, it uses SourceGraph to visualize individual library and code dependencies, which you saw in the bar graph that was flashing by as the build process happened. And it allows us to actually implement debugging so that we can debug exceptions and crashes much more effectively than Arduino ever did, the Arduino IDE. So now that we've got that actually up and running here, let's go ahead and reboot this particular system. And now for this, I'm actually going to take and do a couple of adjustments. I'm going to turn off all the high-speed bits and pieces now so that we can actually get a good indication as to what's happening here. And we'll boot into config. You can see on the console here the individual disk messages happening. And since we're booting into config, you can see the FujiNet intercepts D1 message. And yes, my Wi-Fi password just passed by. Damn it. Okay, so with that, we now have our config up and running here. And we're going to access a particularly problematic TNFS server just to really prove a point. I will not go into detail on the particulars of how this particular TNFS server is connected to the internet. I will just suffice it to say it's on a less than ideal internet connection by far, somewhere on the other side of a black hole. So even with this though, we can see that even here that it's able to handle retries and errors that might otherwise happen. And just to show you what actually might happen here, we will take and load up a copy of, say, Paperclip, for example. Or actually, yeah, do I want to do Paperclip or not? Maybe it'll give me a chance to talk. We'll do read only here. And you can see the commands coming through in slow motion here. But if we hit option, we are now actually going to see, since I set the uncached region to 65535, you can see that it disables the cache, and you're going to see the effects of what happens with that cache actually disabled. And you're going to see just how nutty this network actually is. And you can see right here, even with the cache disabled, it is pushing through, and you can hear each beep individually as it happens. Yes, this is over a long haul link. there's a Wi-Fi connection and power over Ethernet over power line connection involved here. So latency is kind of interesting. It's even more so than some satellite connections that I've seen. I'm hoping that by doing this we can actually see a timeout, so we can see that a timeout actually happening, and watching the code, the firmware, actually recover itself. But it doesn't seem to be happening yet. I speak too close. It looks like it might now. Yep. And you saw there a slight pause there as it took and tried to recover. Now at some point there's a chance that the packet might come back sometime later. If it does, we ignore it because we asked for the packet again. We should almost be done here at this point. This is a large program, but a very nice word processor nonetheless. And we can see right here, paperclip ready to go. And if I were to take and boot it again, you would see much the same thing. Now as a counterpoint, I will now reset the cached region back to 3 and rebuild the result again. You can see because some of the headers changed, some of the other files had to be compiled, but still this was much faster than doing an entire build inside of Arduino, by at least a couple times faster. We upload the result to the firmware, and within a few moments I will take and do a cold start by holding down select and hitting reset on my 1200. We can see everything coming back up. And with that, I hit select, hold down select, and hit reset. This is a feature that's unique to the Ultimate 1 MBs here. This gives us our nice cold start. Now the cache doesn't happen for the cache does not happen for the built-in config, so you don't see that effect just yet. Where you will see it is when I take and mount paperclip again. And you'll notice the behavior down here in the console window will be ever so slightly different as we're loading more packets in. And because this network is, again, less than ideal, you're going to see a certain pause as the tracks are buffered. And this is one thing that I could definitely use some help on for anybody who could help. Basically to try and improve, get rid of the latency in between by re-implementing the cache as a ring buffer. That's first view loaded, and you can see fetch and send off, fetch and send off. And you can see, even with that option there of handling this, drastically increases the speed of the whole performance here. We can make it even faster too. If you'll notice that there is a seek operation happening for, there's a seek operation still happening for every single cache fetch. If we look and we see that the next sector that's going to be cached is the next sector, then we can get rid of that seek entirely, and therefore get rid of having to send and wait for a response for that packet, drastically improving performance. We'll see here that we timed out ever so slightly, but it went, restarted, and recovered. There we go. Paperclip again, running from less than ideal networking circumstances. So I think I'll try one more just to see. We'll go ahead and hit there. Okay. Now we select reset. And we will go ahead and go back to our server here. And for this next one, I will actually pull down and load print shop. Where are you? There you are. Now, since this one turns off the beeps, the only indication that you can see that something's happening is literally with the changing screen. Now, we actually did see here, it looks like we have an end of file. So it looks like there may be still more that needs to happen. And the good thing is that we do have some debuggable information here, and we can see that our seek operation is somehow returning not permitted, so the seeks are not happening to the other parts of the file. I still have to take and see and track down what's happening there and why it's happening. Let's see if we can replicate the problem again, going into cold start. Kind of curious if I actually need to hold down option or not. Okay, so much the same problem here. Try one more time. Okay, so much the same issue here. So it's not exactly perfect yet. Are we erroring out? EOF, we get an end of file, which is interesting. Okay, so as you can see, there's still some more work to do. We'll try one more just to see. Because I have booted successfully, print shop successfully. The difference between it now is actually the cache. So I'm actually kind of curious. If I take and put the cache back, does it suddenly spring to life again? Let's find out. Save, upload and monitor. And if this is the case, then I will take and disable the cache again until we can fully ferret out the problems with the cache. Go ahead and rebuild real quick. Upload the firmware. And with this, go into monitor, take a look, all good. Okay, now let's boot this sucker. The read cache is off, so again, loads are going to be slow over TNFS, especially over slow links, but maybe print shop will load again this time. And if that's the case, then there's an issue with the cache that I have to resolve. Now you can see again, one thing you may have noticed, the cache actually tries to grab sectors in 256 byte increments, whereas the non-cached code will grab the sector in the size of the requested sector size. Why not 512 bytes? Well, because that would be larger than the MTUs of most routers, and therefore the packet would fragment. Again, UDP for you. So 256 is the best size for grabbing sectors at the moment. And we can see that it seems to be going a bit further this time. And I think we should be okay. So basically it looks like at this point, while the retry code is correct, it may very well be that I need to spend some more time dealing with cache coherency, making sure that the cache is valid. Yep, all good. And there we go. And yeah, in artifact color glory there. Okay, so with that, that concludes our status report right now. I'll do another one within the next week or so, showing some of the other bits and pieces that we're working on. Jeff Piepmeyer is actually working on Atari 822 support, as well as Atari 1020 support. So we're increasing our printer scope. We have another contributor, 8-Bit and More, aka Rick, who is testing and working through understanding how the modem handler works. Maybe he can take over ownership of that. And we still have Damasan working on the end device and network code. So with all of this, as with me basically trying to shore up and make the underlying code more robust, I think we'll be on track for a production release by the end of the year. So, until next time, guys, have fun.